And then like you might also
So how do you all the reasons given, right?
Oh yeah. Well, so it's been partly driven by the but the goal would be to think of in the broadest sense. So, if you have any ideas, because you'll still have to scope. If this thing can work on any kind of broad and sort of so the gains are typically smaller. Some possible range. So there's still a lot of room for maneuvering, and the question is, what should that be? I replied to your note, and I sent the copy away. I don't care.
No, I don't care either.
I just wanted to make it. I don't care. I leave that to you. Yeah. No, I understand. That's why our best strategy is really to work as a team.
So what was
We just spoke about animation. That's what I mentioned. Yeah, but he's very interested in artists and dynasty. I don't care if he's good at animation art. I think that's the only one. I think that's I don't think it's like he was asking about kind of waiting till I just explained the process to him a little bit. MIT like this stage off. You totally good. Give me some paper.
But no, I was saying you can make, you can
On this point, are there
To only be tablet makes sense to release the short, unless you were a tablet manager.
part of it? I don't know if it's just me. If the things from that. So, but my point is, as the primary component assigned to me something in GATS, I wasn't getting it.
I actually tested this morning.
So for me, I see no activity. Nothing. Except Jim's email that says, you could be getting the offers out soon. And I'm like, whoa.
I have done all
Like this Oracle.
It's always
Sorry, Oracle.
I used to get notifications saying, I need to sign this to you. I'm not getting any of those. That's a problem. I got an email from GATS, and I clicked on the link and I could get the application. And I'm getting none of those. Right, I mean, so from my perspective, it's like I said, I don't well, I know,
Holger, who's a professor in our department. I think Holger was one of the first people that I met when I came to UBC and started to work closely with. Holger was a postdoc here at the time and has a strong interest in algorithms, as do I. So we found a good intersection of our interests in bioinformatics at a time when not very many people were doing work in that area in our department. As I said, Holger was a postdoc here at the time. He had just gotten his PhD at the Darmstadt University of Technology in 1998, and in fact won a prestigious Distinguished Dissertation Award from the German Informatics Society in 1999 One award is granted to all PhDs in computer science across all of Germany. He was the winner in '99, and then moved on from his postdoc position to a faculty position here in 2000. Now, Holger's research area, what he's going to talk about today, focuses a lot on empirical algorithmics. So presumably many of you have taken 320 and are familiar and love worst case analysis, which is one way to think about how algorithms perform. Well, Holger works on a very different approach, which is to look empirically at how algorithms perform on real data, and then to guide algorithm development also using empirical insights. He's a leader in this field. For example, he's published a book called Stochastic Local Search, which is highly acclaimed. He has won many awards for his work in this area, including a 2009 ICHCAI JAIR Award for the best paper published in JAIR, which is the prestigious Journal of Artificial Intelligence, the best paper published in the previous 5 years. He was a co-author and leading author on that paper. He and his students, and actually Kevin Leighton Brown, Frank is here. Anybody else who's done work on SATzilla? Lynn, great. So they are perennial winners at the annual SAT Solver competition, which is a competition for algorithms that can solve the satisfiability problem. And in addition to advancing the field of empirical algorithmics, Holger has also applied the insights from that work to problems in many other areas, including, for example, software verification. He collaborates with Alan Hu. Also, bioinformatics. He collaborates with me and several others in the department in that area. So advancing the field of empirical algorithmics and then also its applications in other areas. So today he's going to tell us about programming by optimization. I really enjoyed his abstract. If you haven't had a chance to read it, I just want to read the last paragraph. It said, "This talk is not for the faint of heart." I will try my best to convince you that we stand on the verge of a fundamental shift that is likely to affect the way we think about solving computational problems across all areas of computer science and its applications. So that's a good preview for the talk. I do want to mention that Holger also has a singly authored article on this topic in CACM this month, so the talk is occurring at a particularly great time. So if you enjoy the talk, you might want to go check out that article afterwards. Let's give a big welcome to Holger Huss.
Thank you very much, Anne, for this most graceful introduction. Before I begin, I want to say two things in particular. One is that, although, as Anne pointed out, I recently wrote the single-authored paper for CACM following an invited talk elsewhere, which gave me the opportunity to push my own vision of this area quite a bit further than I had before. It should be acknowledged that many of the ideas that you will hear today really come out of long and fruitful collaborations with mostly 3 people and then a whole bunch of others. But those 3 people I want to name prominently. It's my postdoctoral fellow, Frank Hutter, with whom I've worked for many years before he was a postdoc, actually doing his master's thesis and doing his PhD thesis that followed here. Of course, my colleague Kevin Leighton Brown, with whom I've probably worked more than with any other person since I arrived at UBC in aggregate. And my long-term collaborator Thomas Stützler at the Université Libre de Bruxelles, with whom I collaborated very, very closely before I came to UBC and have continued to work quite closely ever since. So I'm very grateful to those folks for sharing their ideas with me, developing ideas jointly, and co-supervising students with me, some of whom are mentioned down here. Not all of these are actually my students. I want to also mention 2 other colleagues, Alan Hu and Kevin Murphy, who have been relatively prominently involved in particular aspects of this work. The second thing that I should say before I begin is that I really do want to warn you along the lines that Anne said. And in fact, what I would say is that the journey on which I am about to take you may in fact rattle some of your long-held convictions and beliefs. And this is entirely intentional. Good. So I want to start with a simple question that everybody here in this room should be able to answer, because this is very basic computer science. We have to sort a list of numbers, stored in a simple array. Which algorithm should we use for that if time is what we care about and only time? What's the algorithm? Any volunteers? No? Yes, please.
It depends on how many numbers.
Yes, and in fact it depends on a great many other factors. It turns out that depends all the way down to aspects of the machine architecture, to the degree to which the numbers are pre-sorted perhaps. So there is no answer. Theory has not come up with an answer to this question in general. There are many good theoretical insights into this that can guide us, but there is no one correct answer to this. Matrix multiplication. What algorithm should we use if we're in machine learning and have to multiply matrices in the context of doing whatever fancy machine learning task? Or in image processing? What should we use there? Any takers? I mean, yes, Mark.
The brute force of n-cubed algorithm, because I can code it without making a mistake.
And many of you will be interested to know that although when you go to Wikipedia or to a textbook, you will find algorithms mentioned that at great intellectual expense and in great intellectual adventures have been proven to be much more efficient than that algorithm. Many numerical algebra libraries for full matrix multiplication actually use that algorithm, the naive one. And they do that because the alternatives, namely the algorithm by Strassen, which is quite well known coming back from the 80s, more recently the algorithm by Koppe and Winograd from the 90s, and as of last year, some of you might remember an email on this topic that I sent around, the latest in terms of in terms of big O notation, the best algorithm by Wasilewska, Williams. All of these algorithms have problems. The last two are completely impractical. They're theoretically very interesting, but impractical for any size matrices that you could possibly want to imagine, not only in the near future, but probably in the next 100 years and beyond. And I have this directly from Wasilewska Williams because I didn't trust my own judgment on this matter, and I didn't trust Wikipedia either. And in terms of Strassen, because of numerical stability issues. And it's the same for pretty much any problem worth talking about. Classification and machine learning, no clear winner, right? So the answer is always, it depends. Now, that should really make us think, right? It should make us think how we go in practice about tackling these tasks, because we do, right? These are very important tasks. And what we learn is that there is no easy answer to these questions. And in some sense, what I'm trying to do in this talk today is to convince you that rather than forcing yourself to go with one or the other, there's actually an alternative, and that is to leverage all the great ideas you might come up with, and then automatically try to find the ones that work best in a given context.
That's the machine learning classifier, by definition.
Absolutely, Nato. And it's wonderful that, of course, machine learning has helped us greatly to address this problem. But I would say this. I would say machine learning alone did actually quite little to address this problem. It provided very important tools, but so did many other areas, notably in statistics and in combinatorial optimization. Machine learning is the key, is one key, and is also one of the great areas that benefit from the kind of developments that I'm about to describe. But I think it would be oversimplified, and I'd be very happy to entertain a lot of discussion on that afterwards to say that this is just a machine learning problem and can or is to be solved as such. That is an approach that has been tried and actually doesn't work very well.
No, I didn't mean that. And I think machine learning is just statistics rebranded with a sexy name. What I was trying to say is you should learn from data.
Absolutely, Nando. There's no disagreement here. The question here is actually how do we enable learning from data and programming, and that's really what I'm trying to do here. So you're jumping a little bit ahead, bear with me, we'll get there in just a moment. So let me now take you back to 1969, to the 17th of July. Does anybody remember what happened on that particular day? Actually, the 16th of July is when things started. It's a great day to remember. All right. Let me show you what happened on that day. So this is original video from the day, and of course it's not great quality. I didn't hook up the audio because this gets very loud. During my last FLS talk, I launched you into space in a very gentle manner. Today it's going to be not quite as gentle. You will recognize this is a Saturn V rocket, one of the most powerful machines and one of the most amazing pieces of engineering outside of computing that has ever been constructed. The only vehicle up to date capable of getting humans onto basically other heavenly bodies, in this particular case the moon. So it is carrying 3 astronauts for the very first time outside of Earth's orbit, and one of them, Neil Armstrong, only 4 days later will become the first person to set his foot on another heavenly body. But the other thing that's riding at the tip of this rocket is actually a computer called the ACG, the Apollo Guidance Computer. And this Apollo Guidance Computer plays a very critical role in the entire mission. It's a rather primitive machine. It runs at only 2.048 megahertz. It has about 4 kilobytes of RAM and a bunch more ROM. And it's basically responsible for all the critical aspects. This is where it goes supersonic, actually, as you can see. It's responsible for guidance and navigation and also control of all the critical aspects of this particular spacecraft. So, of course, since that day, we have come a very long way, both in computing and also in other matters. But I want to take you even further back to 1837, when a man named Charles Babbage, a very noted mathematician and philosopher already at the time, so not just an engineer, started having wonderful ideas about computing. And in 1837, his ideas had reached the stage where he was thinking about what would become what we now call the first Turing-complete computation machine. He called that the Analytical Engine. The engine was not built during his lifetime and still has not been fully realized, mostly due to funding constraints. Most experts in computation and mechanical engineering believe nowadays that what people thought up to about 50 years ago, namely that it would have been impossible to manufacture the device in Victorian times because of mechanical engineering precision limitations, that is in fact false. And with the technology they had back then, given the will, they could have built this computer. And it would have been a Turing universal machine programmed by punch cards, which incidentally would have had exactly the same format as used by IBM more than 100 years later when they started building actual electronic computers. But Babbage was also a visionary. He wrote later in his life, as soon as an analytical engine exists, and we can read analytical engine synonymous with computer, it will necessarily guide the future course of the science. Whenever any result is sought by its aid, the question will then arise, by what course of calculation can these results be arrived at by the machine in the shortest time? So in some sense, he also is the father of complexity theory. And that was in 1864. His work was then almost forgotten for the better part of a century, until Alan Turing, supposedly without having been in contact with any of Babbage's ideas, started reinventing and elaborating that, of course, greatly on some of the same visions. So nowadays, of course, that vision has become truth. This is an article from the BBC News that I actually sent around the department, so some of you might remember it. It's entitled "When Algorithms Control the World," and came out last August. And in this article, somebody is quoted by saying, "The maths that computers use to decide stuff is infiltrating every aspect of our lives. Financial markets, social interactions, cultural preferences, artistic production, education, and the list goes on and on and on." So in all of this, performance tends to actually matter quite a bit. In many cases, computational speed, the very thing that Charles Babbage already was so greatly concerned about, is worth money. In a similar vein, energy consumption is starting to become a major factor, mostly because of battery life, but also because of concerns around sustainability triggered by large-scale computational facilities that are springing up everywhere. And finally, of course, the quality of the results of a computation matter in terms of the cost or profit, or in the case of engineering designs that are computationally devised, the weight of that design, or other performance characteristics. They all have a direct impact on the market. And that is increasingly so because of globalized markets, because of just-in-time production and services, which of course further increase competition, and because of tighter resource constraints that we have to deal with. I want to give you a simple example, and I'll make this a generic resource allocation problem. You can think of whatever is your favorite problem here. I tend to think of the problem of allocating rooms and time slots for exams at UBC because it's a problem that I had the pleasure to work on for a while. And the results of that affect you now, all of you, fortunately or unfortunately, whichever way you think about it, because they're implementing our schedules. But we have a situation where resources, when they exceed greatly demands, there's no problem. And that has been the case in our society in many aspects for a very long time, in that there are many solutions to these resource allocation problems and they're easy to find. When the resources are much, much smaller than demands, this is also not a bad situation because there are no solutions, and that's typically pretty easy to show. And when the resources are about equal to the demands, things can become quite difficult. And it can be also very difficult to show infeasibility of that, of such an assignment of resources to demands. And so therefore, this is where we have to expend a lot of energy on computation actually, in order to figure out in which world we live, in the one where it just fits or the one where it just doesn't fit. Now, the first situation up here where resources outweigh demands is economically wasteful. And the response of the markets to that is typically a reduction of resources or an increase of demand. And as a result of that, we get back into that situation where resources are approximately equal to demand and things get difficult. And in the second case, it's the same because that means if the resources are far lower than demands, that means lost market opportunities and strain within an organization, and that typically means that either we convince somebody to give us more resources or we become more resourceful, or there will be a reduction of demand, voluntarily or involuntarily. And again, we end up in this situation down here. And that is why I believe, and have believed for a while, and I believe I see this panning out around us as well, that the number of computationally challenging problems that we're facing is increasing drastically, and industry's appetite and society's need for solving these problems reasonably well is increasing with it. So in this talk, what I'm trying to do is to discuss with you a new approach to software development, leveraging human creativity, optimization and machine learning, and large amounts of computation and data. I'm sure that Nando agrees with me on the last 2 points, that these are extremely important. I want to therefore emphasize the first point particularly. Thinking about human creativity, this is what has propelled us from Babbage's day up to this point here, right? And I think there is a lot more of it. It's only that we don't make good use of a whole bunch of it. So the key idea behind this talk really is that I want to go from a program which you can visualize by a single point in a space to a large space of programs induced by a whole set of ideas. In doing so, I want to encourage software developers to avoid premature commitment to design choices that nowadays are made very early in the process and lead to fruitful avenues that are never fully explored, and to seek and maintain design alternatives actively to make the space even bigger and even richer. Now, why would you want to do such a thing? It only makes sense if we can somehow navigate these spaces, if we can take advantage of the richness that we create in this way. And that we can only do if we can automatically find performance optimizing designs for given use contexts. And this set of ideas leads to what I call programming by optimization. And that's what the talk is about. So for the remainder of our time today, I want to talk a little bit more about the vision and promise of PBO, about design space specifications, about the way in which we can enrich the formalism that programmers use for expressing the ideas that they have currently in order to capture this idea of rich design spaces better. I will only briefly talk about design optimization. That would be an entirely different talk, and maybe somebody else will give it at some point. But I will tell you enough that you will believe me that this is possible. I will then talk about cost and concerns. One of the greatest articles in all of computer science history, in my opinion, Alan Turing's on machine intelligence, does a fantastic job in anticipating a lot of concerns. And while I would certainly never want to compare myself to Alan Turing, I think I can learn from him in trying to anticipate some of your concerns. I will try that here. And I will finally talk a little bit about the road ahead towards what I hope to become mainstream use of PBO. Okay, so I want to start with a bit of a story, and this is a personal story because I was involved in it. I think the story of how the PBO set of ideas came about would be told differently from different people, but this is what crystallized the idea for me. And that is a collaboration, a collaborative piece of work with Frank Kutter, Domagoj Babic, a former PhD student of Alan Hu's, and Alan Hu himself. That collaboration started sometime in 2006 and led to a publication in 2007. The goal there was to solve SAT-encoded software verification problems as fast as possible. And we can imagine why such a thing would be a useful capability to have, because that would just mean that we could push the limit of software that can be verified, at least in certain aspects, such as null pointer dereferencing in languages that allow such things, and so on. It would push that into more complex programs. So in this particular case, the idea that came from Domagoj and Alan was to build a new SAT solver, which happened to be called Sphere in the end, based on an old idea called Davis, Putnam, Loveland, and a fourth L that I always tend to forget because it's just the fourth person that in that particular set. But anyway, this idea has been guiding the construction of good SAT solvers ever since the 1960s, and Domagoj decided to follow that idea. And he ended up generating a rather highly parameterized heuristic algorithm, because these algorithms, although they are complete, are heavily driven by heuristics. He looked at a lot of the SAT literature and pulled out all the ideas that seemed to be good and integrated them there, which turned out to be easy because these sets, these ideas in the same framework work quite well together, at least at the level of implementing them and playing around with them. Now, do they perform well? Who knows? So this led ultimately to a solver with 26 parameters and an astounding number of over 10 to the 17 configurations. And then Domagoj went as you would and configured this manually, and it took him a week, and he got some performance that looked pretty promising, and that was that. And there would be nothing particularly exciting about the story up to this point. But then something extremely interesting happened. He met Frank, who at this time was a PhD student at the department. They started talking, and Frank had been working with Thomas Grützler and me on an automatic configuration procedure named Parallelisation. I will talk a tiny bit more about that later, which basically can solve this generic problem of configuring an algorithm for optimal performance much better than similar procedures that had been around previously. So it really pushed the boundary on that quite a bit. And so when Domagoj started using that, I think in the beginning he was enthusiastic but also mildly skeptical, and he saw that this somehow worked. And in fact, the first version of Sphere didn't even have 26 parameters. I shortcut the story a little bit there, but it only started having more parameters when Domagoj went like, wow, now I can finally enable these other things that I had thought about and implement a little bit more and see whether perhaps this would be useful. And lo and behold, some of these things that previously in his manual playing around could never be shown to have any benefit started making sense in certain situations. So that's what I see as at least one of the points where the PBO idea really started crystallizing out very clearly, because he was a software designer, somebody who had become a domain expert. And he went like, I had all of these ideas that I thought I really couldn't meaningfully put into my design. And with this tool in hand, all of a sudden, I'm no longer forced to abandon them as prematurely or never explore them. So here's in a nutshell what happened. Minisat 2.0 was the state of the art at the point. Out of 302 test instances, and they were null pointer dereferencing problems from various pieces of C code, quite a few of them real world actually, such as compression programs and I think an internet daemon and so on. That solved all of these problems on an average, in an average runtime of 161 seconds. So actually not so bad. And that was the world champion in SAT solving at the time. And that algorithm was actually built particularly with verification problems in mind. Hardware verification, not software, but you take the best you get. So the original version of Sphere, hand-tuned by Domagoj, the actual developer and domain expert, solved almost all of these instances within a generous cut-off time, and it did so on average in 787.1 CPU seconds. And you will say, wow, this is like 5 times worse than the world champion. But then Domagoj was a PhD student that had only started working on SAT solvers like half a year or a year ago, right? So he really didn't play in the same league as the guys that had spent years and years building Minisat. Then we configured it automatically, and the average time dropped down to 35.9 seconds. So that was a big, big surprise to everybody involved that it would work out that well. And then we thought perhaps software verification is different enough from hardware verification that it's worth configuring it just for software verification. And of course, knowing at least a little bit about machine learning, we would never train this on the data that we were testing on. So we did these 302 instances here that we used for evaluating state pristine. We used a completely different training set, and what we found is that we could get that CPU time down to 1.5 seconds. So that's a 500-fold speed up through the use of this automated algorithm configuration procedure, and was confirmed as the new state of the art in the 2007 SMT competition in the category into which the problems that we were optimizing for actually fell. So that was very nice. But I want to emphasize the key here is not just that we managed to get that automated algorithm configurator going. The key was that Domagoj himself, once he had the tool in hand, said, now I can be creative about this. And that's the key idea behind PBO. Good. So how does software development in this future world of PBO that I imagine actually work? I imagine a group of people who work together on solving a certain problem and doing that by writing programs. So they will produce what I call a PBOL source, where L is a language of your choice. Think Java if you want, think C++ if you want, think Scheme if you want. Then there is a tool called the PBO Weaver that takes this enriched source and spits out two pieces of information. It spits out what I call a parametric source, automatically generated from this PBO source, and a design space description. These, together with benchmark inputs characteristic for a certain use context, become input to the PBO design optimizer. In the simplest case, this could be an algorithm configurator, but as we will see later, it could also be other things. And that will then produce an instantiated source in your target language. And that instantiated source in compiled languages can then be compiled and deployed as an executable. That's the idea. And the beauty of this idea is that if these folks here make a rich design space, and this tool here is good enough in doing the optimization properly, and we have good enough data here, we can do this for a large number of use contexts without ever going back and revisiting this design. So PBO can take various forms. I tend to think of levels. Level 0 of PBO is to optimize settings of parameters exposed by existing software. And I would liken that to a hot air balloon. It's a simple device. It takes a bit of skill to get this thing going and to get the limit where you want, but it can get you very high. In level 1, you would go a little bit more ambitious. You would expose design choices hardwired into existing code, such as magic constants, hidden parameters, and abandoned design alternatives. And actually, if you take any sophisticated piece of code and you break it up and you look into it, you will find plenty of these things in there, right? So that again is something that doesn't require major departures from what you've been doing anyway. It takes an existing piece of code. I would liken this to a little motor plane that can go a little bit further than the balloon under most circumstances. The next step would be to keep and expose design choices considered during the software development process, to basically say, this here didn't seem to lead anywhere, but not for reasons that I now understand well enough to really discard it for good, because I'm sure that it could never do anything good for me. But just because you go like, doesn't seem to work as well as this other one, might be expensive to keep around, let's ditch it. And this says, no, don't do that. Keep these around, because they might still be useful. And this gets us into the jet age. The level of that would be to strive actively to basically tell the people that you're working with to strive and provide design choice and alternative. Make more, be more creative about this, right? And that would get us into the rocket age. And beyond that, it becomes very speculative, as you will see in a moment. And that would be to make it a religion. And that would be to say, make no design choice prematurely that cannot be justified compellingly. Where compellingly might refer to money, to computational theory, to whatever, the mood of your boss in the morning, perhaps the latter not, right? But we haven't been able to construct work drive yet, neither in my group here nor elsewhere, but I think ultimately it might be possible. In case you're wondering, this model here actually stands in Malton, Alberta, a place for fans of the series probably worth visiting. So How successful can this be? Let me just give you a little overview. So success in optimizing speed, I already talked about speed-ups between 4.5 to 500 depending on use context. And the 4.5 you achieve in use contexts that are very similar to the ones that have been considered in hardware verification by the SAT community for a long time. And as it turns out, these are quite different from software verification. And this is PBO level 2 to 3 because Domagoj actually did go and actively look for new things to try out after he saw that it worked. There's AI planning, which Chris Fawcett and I, together with collaborators in Italy at the University of Brescia, recently published on, where we achieved speed-ups between 3 and 118 at PBO level 1. So this was just by exposing things that were already there but not exposed previously. And that had 62 parameters, so it was in some sense a lot more ambitious in the end. And finally, perhaps one of the most impressive examples, although the speed-ups are not the most impressive, but because it's a piece of highly optimized commercial software that is used by thousands of big companies and universities worldwide, perhaps the most widely used practical optimization tool, the mixed integer programming solver Cplex, on which together with Kevin and Frank, we've achieved speed-ups between 2 and 52 at PBO level 0 by just configuring what was already there. And that wasn't because we believe that PBO level 0 is the best thing to do, but because IBM is still reluctant to let us look under the hood of this thing before we demonstrated that we can do it at this level. And so this is very interesting, and in fact, in results that have not been published yet, we've recently seen speed-ups of Cplex on problems related to computational sustainability and forest resource management up to factors of 5,000. Okay. And we are working with IBM on that, who, when they first heard this, were absolutely astonished that something like this would be possible just by configuring their solver. Solution quality also works well. University timetabling here at UBC. We have a solver with 18 design choices exposed at PBO level 2 to 3, and that is a new state of the art in solving academic university timetabling problem, and we had the good fortune to be able to transfer this into practice here at UBC, and as I said, joint work with Chris Fawcett here at UBC and Marco Chiarandini at the University of Southern Denmark. This is what UBC is now using for scheduling exams. So if you don't like your exam schedule, come to Chris Fawcett. So, PBO enables performance optimization for different use contexts. I've already argued how that would work, but you can go much further. And in this talk, just because of time, I want to only briefly outline that. You can adapt to changing use contexts. Think of overnight, perhaps you get a new batch of problems in, you can retrain, of course, and find a new winning design on that. And so this is a really nice instantiation of an idea that Sebastian Thun calls lifelong learning. You can possibly use it for self-adaptation while solving a given problem instance. This is a very intriguing direction that hasn't been as much explored yet as it deserves, but certainly we'll hear more about that in the future. You can pursue an idea that Kevin Dayton Brown and I have been exploring together here, and other people elsewhere have done it as well, namely to generate instance-based solver selectors that have a whole bunch of designs for which they select on the fly when the instance comes in. And all of these individual solvers can be configured using PBO to work not only well individually, but work well together. And finally, you can automatically generate parallel solver portfolios. This is something that Kevin and I pursue currently jointly with a PhD student in Germany and his supervisor, Thorsten Schaub. So briefly about design space specification, if you were to buy into this and drink the Kool-Aid and think PBO is it, right? So what would that look like for you as a programmer? Well, option one is that you just use language-specific mechanisms for specifying your programs. And what that means is you expose command line parameters, you use conditional execution based on the settings of these, and maybe if you have a language that supports that, to be more efficient, you use conditional compilation. Okay? And with that, you can easily do all the way PBO up to level 3, but it's tedious. And that's the reason why there are magical constants in code, because it's tedious to even expose one parameter in most languages.
Holger, today is there any real difference between conditional execution and conditional compilation if the compiler can see the constant?
I believe in the C++ programming language, at least there still is. Because I believe that most compilers, and maybe all compilers, but I'm no expert in it, are not strong enough to reason through all the cases that, the explicit declaration of conditionals allow you to handle. But it's a fair question whether in the future this might blur more and more and ultimately might disappear. But I think it hasn't disappeared yet, and I've seen evidence for that. Option 2, of course, is to be a little bit more ambitious and to have a generic programming language extension. Option 3 would be to have programming languages constructed just for this. And I'm not going to talk about that because I think option 3 is not a realistic option. But option 2, I think, is. And what you would have there is dedicated support for exposing parameters, for specifying alternative blocks of code, and for exposing information about the state of the algorithm at runtime in an efficient way. So what are the advantages of going that way? Well, first of all, I would argue that it reduces overhead for the programmer. And you will see an example for that in a moment. More importantly, I believe that it allows you to cleanly separate the design choices from other parts of your code. And I think that's actually very important. And thirdly, dedicated PBO support in software development environments I think will be key to the success of this. And I think that can only be enabled by declaring the PBO content of your design explicitly. And that is best done by using new constructs. So the key idea here is to use augmented sources where PBO Java, for example, would be Java plus some new PBO constructs, and the PBO constructs would be the same regardless of what programming language you use. And then you would compile that down, this enriched source, into the target language, and the tool that we use for that, for the lack of a better term, and in a rather deliberate nod of our heads to aspect-oriented programming, we call it Weaver, because it basically weaves sources together. And so let me briefly talk about what these PBO-L enriched sources would look like. So it's this part of the diagram here. So here's a piece of code that I wrote myself during the time when I was a postdoc here, as Anne said, and you can see it has a magical constant right here. So what would I do about that in PBO? I would simply introduce this one line, and this can be anywhere in the code, ideally directly before that. This basically says there is a new parameter, it's a floating point thing, it's set to 1.4, and it's referenced here. This is dead easy. They can appear in arbitrary places before or after the first use to be really flexible. The access to them is read-only, so that the values can only be changed via the command line or some configuration file. There's deeper reasons why this is, I think, a very necessary choice, and that's all there is to it. And you would go like, wow, that's only a few lines more than it would be, a few lines less than it would be in the traditional way. But these few lines actually matter. And I would argue that using this way, people would be much more likely to expose a lot of parameters. But much more importantly, how do you specify design alternatives? And that's the really core of the idea. And there's this idea of choices, which are sets of interchangeable code fragments that represent design alternatives. And these design alternatives are called instances of the choice. And what you should think of here is just two blocks of code that functionally do the same thing at the level of specification that you're interested in when reasoning about correctness. And now the question is, when I get to that point, which one should I execute? A choice point, then, is a location of the program at which a choice is available. And so here's a little abstract example. So this basically says that there is code that can be used for pre-processing, may or may not be used, and it's in here in this block, and it's declared like that. Now, it might be that I have more than one way of doing the same pre-processing, and then I would have one block here and one block there for the two modes, and they would do interchangeable things, but possibly with rather different efficiency. And of course, I could also have the same choice here giving rise to instances at more than one point of the code. So if I do my pre-processing here, maybe I need to do some cleanup here. And that is all very naturally done as well. And finally, you can nest this construct in that when I do pre-processing, perhaps I want to optionally do some extra pre-processing, and I do that in here. So you can see that this gives rise to a rich little extension of the language. But it's not a big deal, right? I mean, after I told you this, you could probably start using it. It's not a complicated idea. So now we need to weave this, so here comes the PBO weaver into play. And of course, you can already imagine this is very easy. It transforms this PBO-L code into L code, where L is some language. It has two modes, and that's very important for efficiency. One is the parametric mode that you need for configuration, and that's why conditional compilation would not work with that. Because that's where you expose everything for parameters, you make choices accessible via those parameters, and then you configure, okay? But after you figured out a configuration that works, or perhaps if you want to deploy it in a use context where the customer hasn't paid you for the full richness of your space, but only for parts of it, right? You might want to do instantiation or partial instantiation. That means you hardwire back some of the parameters and choices into your code and expose others. And that can get you all the way down to a source that leaves no trace of all the richness that gave rise to what you've done. And then you can make this code freely available on the web and have people play with it and still sort of protect the richness of your space that way, which is a nice thing to be able to do. So let's briefly talk about design optimization. That is a topic that I've talked about before. The complexity monster, which we've seen perhaps in a previous talk, makes a little reappearance. It's not that scary anymore, so we don't need to spend quite as much time. It's actually a cute little color, and we know how to deal with it. I'm only going to talk about the simplest case, which is configuration and tuning. You might wonder why you can't just use standard numerical optimization, such as the award-winning CMAES algorithm, currently the best numerical optimization algorithm in practical terms available. And the answer is these problems are just too different, right? Primarily they're different because when you actually optimize over these typically highly discrete spaces, configurations that are not good cost you a lot more to evaluate than configurations that are good. And that makes it, that is exploitable, and standard optimization techniques don't. There are advanced resampling methods that work quite well. There are so-called racing methods that have their limitations but also work quite well. There's the family of model-free search, into which the Parallelisation algorithm that I mentioned earlier and will explain at least in some detail in a moment falls. And finally, there's sequential model-based optimization. This latter one is a very promising, heavily machine learning type approach that has been first pushed by statisticians, later adopted by optimization and machine learning people, and has now, as of recently, primarily through work in our group, reached a stage where it's very competitive with model-free and often outperforms model-free. It has certain advantages and disadvantages that I don't want to discuss here, but it's certainly a very interesting and very strong model. So iterated local search, which is a model-free method that is very easy to explain how does that work, only so you get a glimpse how you might do that. And of course I'm highly abstract here, so I'm not showing you a 60-dimensional discrete space because that would be difficult to visualize, right? So I'm showing you something smooth, and so we initialize somewhere in the point, perhaps at our default configuration of some algorithm. Then we do local search, where we just greedily optimize individual parameters to improve performance, and of course that can get stuck in local optima as seen here, at which point we initiate a so-called perturbation, which just disrupts our solution and gets us elsewhere, typically worse. From there, we do another local search, which we hope will get us into a better place, but of course there are no guarantees in that high-dimensional world, at least the way we're doing it here. We have memorized this local optimum, we compare it to this, and then select between the two of them using a simple acceptance criteria, and then iterate the whole thing from there. Very simple. You could go and implement that in less than an hour, and it would actually work. How do you use that for design optimization? Well, once you've exposed everything as parameters, which the PBO Weaver does for you, you can then do this iterated local search in configuration space, in the parameter space of your program. We initialize that typically by picking the best between the default and a certain number of random configurations, just in case the default hasn't been chosen wisely. Our local search procedure that gets you to local optima is an iterative first improvement, so whenever you find an improving step, you actually take it quite greedily, and you don't look further around whether you find a better step, you change one parameter each step. Perturbation, very easy, take S random parameters and just set them to something else. Obviously one could do a lot better here, but this tends to work well enough. And acceptance, just select always the better of the two. It's a very simple algorithm actually. When you implement it, it becomes a little bit trickier. Frank has a lot of stories to tell about that. But still, this is not rocket science. The one thing that deserves special attention is that the number of runs per configuration increases over time. And that is necessary in order to ensure that incumbents always have the same number of runs as challengers, and that in fact you don't throw too many things away based on limited information. But at the same time, you don't want to spend a lot of time evaluating things that already look like they're going to be bad. So, and this works. As I've shown you, all the examples that I've shown you earlier are for Parallelisation. So you can see that even such a simple procedure works amazingly well. And rather amazingly, even with a lot of exploration, we haven't found anything yet that is, say, orders of magnitude better. We have things that in certain contexts are somewhat better, and we hope to improve them even further. But then to be fair, this could also be further improved. So expect to see even more powerful design optimizers in the future. Costs and concerns. We're nearing the final stage here. So you might ask now, what about computational complexity? I mean, this design optimization, I'm telling you it works, but that's still a costly thing, right? What about the cost of development? Will people really want to adopt an approach where they have to maintain not only a code base that has the bare minimum that you need in order to solve the problem, but a whole of other stuff that may or may not ever get used in the context that make you money? And is this in the end perhaps limited to problems for which we really don't know how to solve them well, meaning NP-hard problems? Or is there room for applying into problems for which, like the ones that I mentioned at the beginning of my talk, for which we really want polynomial time and half polynomial time algorithms? So let me take them one by one. Computationally too expensive. So let me revisit the example of Spear. The total configuration time on the software verification benchmarks, I didn't tell you that before, was about 30 CPU days. The wall clock time on a 10 CPU cluster, because you can do that, we do that with 10 independent configuration runs of 1 day each, would be 3 days. So you have to wait 3 days until you basically get that improved design. Now, the cost on the Amazon Elastic Compute Cloud for those compute cycles happens to be $61.20 US. And when the euro was still a little bit more robust like now, right then now, this was 42 euros and 58 cents. Now it's maybe 50 euros, not quite, probably a little bit less. But you can see that for the US, we actually have the data. We know how much that pays in terms of an average software engineer. That pays for 1 hour 45 of the average software engineer. And by the way, it's shocking to see that software engineers make so little money in the US, but those are official numbers that I just pulled the other day. At minimum wage, which should shock us even more, this would buy us quite a bit more, 8 hours and 26 minutes. But I don't think at minimum wage anybody would really achieve improvements on this particular design. And I also happen to think that no software engineer would achieve these kind of improvements within 1 hour and 45. Okay? So this is actually pretty cheap. Secondly, too expensive in terms of development. While design and coding, there's clearly a trade-off between performance and flexibility on the one hand side and overhead on the other. And the constraints of any project will basically drive this. But I say that in examples like Spear or planning or UBC timetabling, if you would have abandoned the design alternatives that ended up surprisingly working well in the end prematurely, you would have lost a lot of money and a lot of people time working with these solutions later on, downstream in the process. The overhead also depends on the level of PBO. PBO level 0, the overhead is almost free, and at level 1 as well. As you go higher in the hierarchy, of course, it becomes more and more expensive, and you want to make sure that your use context warrants that. But most importantly, the traditional approach also has a huge cost, and that is often hidden in that there is a significant phase in many performance-critical software engineering projects where there's manual exploration of design choices. And that's just a very inefficient thing to do, because typically that is done by the designers of the performance-critical components. These are highly paid experts, and they use the time that they could otherwise use for thinking about better mechanisms for basically exploring the design space that's already there. In terms of testing and debugging, the key insight is that design alternatives for individual mechanisms and components can often be tested separately. Certainly in terms of simple types of analysis, but also if you assume that there's only weak dependence on them, in the sense that they are really semantically equivalent, you can write unit tests that just apply to everything. And that makes the effort linear rather than exponential in the number of design choices and makes the whole thing manageable. The second argument I would put forward here is that software testing is an area of empirical computer science that has been neglected for a long time, but for the last 10 years has seen amazing progress. There's now an amazing array of really powerful automatic methods for testing, and they're quite effective. And these are the methods that I think would work particularly well in the context of these design spaces that you encounter in PBO. Finally, is it limited to the niche of NP-hard problem solving? When I first submitted the CICF paper, one reviewer basically said, this is all really nice, but it's just for a niche, right? It's just for the few people on the planet that need to solve NP-hard problems. And NP-hard problems are really kind of rare in software engineering, right? I don't think they're that rare, but even if we believe that, there's plenty of evidence in the literature that it's not limited. And in fact, I call this PBO flavored work because it follows the same intuitions, but never basically formulates the vision quite in that way, in that general way, and certainly never goes into supporting design space specifications. So Whaley et al. In 2001 already showed that computing platform-specific performance optimization could speed up linear algebra routines, basic linear algebra routines used in a ton of contexts very significantly. Lee et al. In 2005 showed that the optimization of sorting algorithms using genetic programming really does result in sorting algorithms that work better in practice when you have big sorting problems. And finally, Pan and Eigenmann in 2006 and Cavazos et al. In 2007 showed that compiler optimization, which is already sort of a meta approach, right? Because the goal there is, of course, to have the target that you are optimizing the compilation for be more efficient, that compiler optimization also benefits from this approach very drastically. And then finally, in the area of databases, Diao et al. In 2003 showed that by automatically configuring a database server using very primitive optimization methods, actually, you could get huge speedups in a fairly realistic model of an e-commerce application. So all of these, with the possible exception of compiler optimization, are polynomial time problems. And in all of these, the PBO flavored approach worked really well. Good. Now, let me conclude and leave a little bit of time for discussion. What I want to say here at the end is, first of all, as computer scientists, it's always very important to remind ourselves that as algorithms and computers control the world, our responsibility increases. And the reason that is the case is because what we're doing in more and more difficult to understand ways create and shape and manage the world around us, right? They create our experience, they mediate our social interactions, and they really have an influence on how the world works and how we work in the world. And that is very important to keep in mind because much of what we're doing is, of course, intended to improve our ability to manage things responsibly and to make good use of the resources that we have. An amazing example of making good use of resources that I saw recently, and probably you all saw it too, is this particular one here. So this is the first Lego man at the edge of space, launched there by two 17-year-olds from Ontario on a budget of $400 using a helium balloon and a custom designed rig that they just came up with on their weekends. That wasn't even a science fair project, they just did it for the heck of it. And that, by the way, compares to one of the Apollo missions, Apollo 11, at about $2.2 billion nowadays dollars, right? So 400 gets you to the edge of space. If you want to go to the moon, it's quite a bit more expensive. But what you can see here is that with little resources, you can do you can go very, very far if you are willing to think outside of the box. And then you have an amazing view from up there, as you can see in this particular slide. Now, the road ahead for PBO, I feel we're somewhere near the edge of space, right? We're not on the moon yet. I hope this will happen, but we still need to work on those rockets quite a bit, and on the work price specifically. But I think what we need to do is really provide good PBO-based software development tools. And there's actually two undergrads with whom I'm currently working on that, or actually I shouldn't say undergrads, because at least one of them is already graduating, the other one is about to. So those are Quinn and Steve back there. They're working actually currently on various PBO tool support. In particular, Steve is working on an Eclipse plugin that should be available on the PBO webpage very soon, and Quinn is working on Weavers. We have Weavers for PBO-C and PBO-C++, and one that almost works for PBO Java. Hopefully with Quinn's help we get that last one working too. We have the Eclipse plugin almost ready to go, and Steve will be continuing to work on that. So this is geared to what's happening in PBO, where development platform and Eclipse seems a good choice there. And we have improved PBO design optimizers already, but we want to have an integrated optimizer that's easy to use, and that's also something that Steve has started working on. We need best practices for this, right? We need to know which kind of design optimization to use where, and how to most effectively make use of these language extensions. And maybe the language extensions that I currently propose are not the right ones in the end. So there is work to be done there, clearly. And I think we should have many further applications, and let's show over and over again that this actually works. Finally, I think we can get a lot of scientific insights out of using PBO, and let me just spend 20 seconds on that by saying the way that now empirically people assess whether an ID works or not is that they implement it and benchmark it and basically have a little horse race, or a world championship in SAT solving or something like that. But I think it's actually much more effective to evaluate ideas by saying, if I throw this idea into the big design space and then optimize the design in the presence of this idea, how much does the presence of this idea give me over what was there before? And that's a different question. I think it leads to deeper insights. My final word will be on leveraging parallelism. This is something, of course, that is very much on all of our minds, I'm sure. And I want to make the argument that PBO is coming sort of to a certain state of at least usability at a very opportune time. And that is because PBO gives very natural and very strong ways of leveraging parallelism. First of all, parallel programs tend to have naturally more design choices than sequential programs. And that's because the interaction that governs the various components typically is subject to various ideas that could govern that, and therefore there is design choices there. Secondly, in PBO, as I mentioned previously, and that's something I'm exploring with Marius Schneider and Thorsten Schaub in Potsdam and with Kevin here, it is in principle, it should be possible to derive parallel programs from sequential sources by simply making more than one configuration and running them independently on multiple cores or multiple computers. Right? So this is just running the design optimizer, perhaps just multiple times, perhaps just once on the combined space of these, or perhaps in a specific modification where it tries to make things that also work well together, even in this independent run setting. And that is something known as parallel portfolios. There's evidence in the literature that this can work very well, and deriving them automatically from a sequential source I think would be very exciting. And we are starting to see some promising hints at least at results. And finally, and perhaps most importantly, you know, Intel and the other hardware manufacturers are pretty worried about how can we make use of all of this computation. And one answer to this is, of course, non-linear, it's machine learning, right? Big data. But the other part of the answer is, if we manage to find a way of turning CPU cycles into something that makes existing software better, that would be a great use. Because we spend the CPU cycles, and a huge amount of them, perhaps once, and then we get something that amortizes that over and over and over again. And that's the idea that leads to you know, first of all, using PBO in general in this area, but secondly, to actually designing parallel design optimizers to more efficiently get to the stage where we have an optimized program. And actually, Frank and Kevin and I have been working on that and just published a paper that indicates quite strongly that this is very possible. So let me wrap up by saying that I believe that programming by optimization is an approach that can leverage computational power to construct better software in the sense of better performance and better flexibility. It also enables creative thinking about design alternatives, something that software developers probably will like, at least in our experience they do. That produces better performing and more flexible software, and finally facilitates scientific insights into the efficacy of algorithms and their components, and also into the empirical complexity of computational problems, essentially because it allows us to get better empirical bounds. So I really hope and believe that this can and will change how we build and use high-performance software in the future. I want to close with acknowledgements. There is a large number of collaborators. I've colored the ones in blue that are here at UBC, and the rest are collaborators that are now elsewhere. And a number of fun and very smart colleagues that I've had the great fortune to work with. Once again, I want to draw particular attention to my long-term collaborators, Kevin and Thomas, shown in blue here, but there are many others who are invested in this effort. And finally, none of this would have been possible without very generous research funding from NSERC, 2 NCs, M Prime and Grant, from NCI, from CFI at the very beginning, and from 2 companies, most notably perhaps IBM recently, and computing resources locally at ISIS and beyond. Compute Canada and Westgrid, I should say specifically nowadays, is something without which we couldn't do any of this research, and I'm very grateful that we have that available. So this is my last slide. I always like to conclude talks with a provocative quote. This one here said, "Gli uomini hanno idee. Le idee se sono allo stato puro sono belle, ma sono un meraviglioso casino. Sono apparizioni provvisorie di infinito." This comes from an Italian novel that I very much enjoyed reading. You can read my English translation. There are people in the room who can perhaps correct the English translation as well. But I really hope to have given you today not only an impression of an amazing mess of ideas, but something that could potentially become beautiful and perhaps offers glimpses fleeting apparitions of something far beyond. Thank you very much for your attention. Yes, David.
So, people who look at the high-level programming languages, sort of extremely high-level programming languages, have similar arguments that you really want to have a specification of the problem and let the computer optimize it. When you dismiss that and you try to argue for programs that require you to do a whole, once I've written a Java program, I've had a whole lot of design choices in sequentializing it. So I'm just wondering.
That's a very good question. So the question is really about program synthesis, because that's the name that's often used for this, right? You write a specification and then something keeps churning and makes perhaps a performance optimized program out of that, right? So David, you might actually know more about the latest in this than I do, but my impression is that this is a lofty and certainly very worthwhile goal, but one that we are very far from achieving in any satisfactory manner. I think if we ever achieve it, and I have no doubt that this will happen, perhaps later rather than sooner, I think design optimization techniques such as the ones developed currently for PBO will be absolutely essential to do the performance optimization part of that. And I further believe that there is a fundamental obstacle on the way, and it's not me who came first up with this idea, but I like the idea very much. And that is that coming up with a good, clear specification of a problem is essentially often as difficult as coming up with at least a simple program to solve it. And so in terms of making correct programs, that has been, as far as I understand, a limitation in this entire approach. And I would think in terms of performance optimization, you start getting into similar limitations. Now, this is not to say that, a long time from now, I wouldn't think we might have a state where we don't have to think about programming at all anymore, right? Where we basically just say, computer, sort the numbers. And the computer sorts the numbers and we're happy, right? I just think in the meanwhile, until we get, that's not just work drive, that's way beyond. Until we get that to work, PBO is a pretty good thing to have. And so maybe it's a stopgap solution, but a good one. David.
I know you're also interested in bioinformatics, so there's famous problems like protein folding and drug design and so on that are compute bound. So can you apply PBO to problems like that?
Absolutely, and we have at least a little bit of evidence for that, and I'd love to see more. Chris Stachak, I think, is in the room. Chris, you could answer the question just as well as I do, because quite a few years ago, you and I worked together on a somewhat abstracted protein folding problem that nevertheless captures the full computational complexity of what is believed to be the one of the real problem. And we used essentially PBO level 0 to get very good speedups over what was the state of the art then. Why haven't we taken that and made it work for the drug companies? Well, it turns out in order to do that, you have to learn a lot about realistic models of protein structure. And both Chris and I decided that that wasn't how we wanted to proceed at this particular time. But I see no reason why this shouldn't work great for many bioinformatics problems, because bioinformatics, like you say, is full of NP-hard problems. And NP-hard problems are the ones where experts can come up with very different ideas of how to solve them that really work well in weird combinations, right? And in that vein, I think PBO could probably work wonders there. So it would be great if somebody other than me would pick this up and do a little bit more work on it. And maybe I'll get back to it too. Nando.
So I think this is all fantastic, and I also think there's nothing controversial about this. People should be doing. People have been doing this for a long time, except that they've never actually formalized it and have taken it in the extent that you guys are pushing it. The idea of using, say, hierarchical basic models where you're introducing hyperparameters and which are just tuned parameters.
Yes.
Parameters to tune the ones down. It's been explored for many decades.
Mm-hmm.
But at this level, I think you guys are doing new stuff, and I think it's pretty amazing stuff, and the right way to go ahead. But in this, there remain some challenges. There's 3 challenges I can think of. How do we deal with higher dimension? Because I don't think all problems in life can be dealt with 100 dimensions in terms of design.
Yeah.
What if the objective function doesn't exist? Or what if that objective function is NP hard to actually obtain just a single sample? And like mixing of Markov chains is one such example. And the other thing is, the tuning, you design the tuning algorithm, so there's choices there. Do we start making choices of choices, and if we do this recurrence, I believe there could be some stability, but this is the problem that the hierarchical Bayesians had to answer every time they give a talk. What happened? How far up do you need to go?
Okay, excellent. So Nando asked 3 questions. As a believer in PBO, I'm just going to pick one of them. Optimize my answer for one of them. And I'm going to choose the last one because I think it partially subsumes the first one, and I also think it's intellectually a very interesting one. I'd be more than happy to answer your second one later. So, you know, how about sort of higher level meta optimization and so on? And it turns out that Kevin and Frank and I have actually done that for Parallelisation. There are many people in combinatorial optimization that believe that as you go to higher and higher meta levels, the payoff is going to be smaller and smaller. I used to believe that as well, in the sense that the underlying software tends to become more and more robust to these hyper and hyper parameters and so on. I used to believe that. I'm not so sure anymore. I now think that, you know, at this first meta level at which PBO currently is aimed, right? I mean, PBO doesn't say stop there. It just says this is something you can do. And it doesn't talk about going to higher levels, but you could. But at the first level, there is so much benefit to be reaped already that I think we should go after this first. One level higher up, the evaluations will become very costly, which is essentially also your second question, incidentally, right? Because now you have to evaluate the performance of a configurator, and what that really means is that you have to run the configurator on many different designs and so on, right? So you optimize the optimizer. And while that has been done successfully in some cases, not only ours, but also in terms of numerical optimization algorithms, they have been automatically optimized using tools like ours. In general, I think this is still so expensive that we're a little bit computation bound there. I think that will change. My prediction now is that within 10 years we'll be at the level where people do meta optimization routinely, and where it will be worthwhile in many contexts. Now, how high up does this go? I don't know. I think that's a wide open question, but what I firmly believe is that at the lowest level alone, the benefits would be sufficient to motivate me strongly to go after that, even if somebody told me that one level higher up, everything collapses and it doesn't work anymore, and you're back to using your intuitions. Mark.
I have a question back, I think it was at slide 30 or 31 when we were talking about the issues of software development with people.
Okay.
And the testability one.
That one?
The forward one, maybe? There's something about, there we go.
That one?
Hit it. The testability question. And I'm skeptical about that one, because software developers, in principle, would like to define our interfaces so that everything is interchangeable with respect to the interface.
Yep.
And that occasionally happens, like things with the Java API that are incredibly carefully designed by really, really good programmers with lots of checking. Real programmers on most things aren't really as careful as that. And in fact, the big advantage of PBO is supposedly that it can find configurations that the programmer had never thought about.
Yep.
Which seems like just heading right into the quicksand of, yeah, we're going to find the thing that nobody had ever thought about and is going to cause some error that no one had ever considered.
Right.
So how do we make sure that we're not going to blow up the software when we design configurations that the programmer had never imagined?
My answer has 2 parts. The first is, we've actually been there and seen that. Frank actually found errors in commercial software, like just bugs that the developers didn't previously know were there, and high-stakes commercial software as well. So, you know, he also found improving configurations, and sometimes the ability to automatically find errors is actually worth a lot. So I could humorously say PBO might be a great debugging strategy, even if you don't believe the rest of it. But the second part of my answer is, of course, I believe that there's more. And you know, I think in fact you're right that software developers tend to be still a little bit sloppy about interfaces and specifications and so on. If PBO works, that might provide a large additional incentive to become more careful about it. And I think in principle the cost of becoming more careful is not that high. If you think of unit testing, for instance, unit testing for design alternatives would work out of the box, right? You just have code coverage in your configuration space, and code coverage is not difficult to get, right? That's polynomial, that's linear time. And you just run it. And your unit tests will just work. They might uncover more stuff than if you just had one execution path or one configuration path. And that's part of the added cost of PBO. And that's where you have to sort of judge the benefit of maintaining an alternative. But in principle, I think perhaps with slightly modified and adapted software engineering techniques, this should be manageable. And I do think that, of course, you could push it one level further where you go this assumption that I'm making that all the design choices are semantically interchangeable except for performance, that you drop that, right? So then we start to go into the gray zone between PBO and program synthesis. At this point, you're immediately in deep water. Which is not to say that some of the techniques that we've been developing here might not be useful still. But it's not what I talk about when I say PBO. And I don't think we have to go there in order to do neat things. David.
One last troublemaking question. So I'm amused that you call your system lead oxide, seeing lead was apparent. I've heard that lead was one of the causes of the downfall of the Roman Empire. Lead poisoning causes your mind to go, neurological damage and cause your mind to go slowly.
Will the lead in the lead oxide fry your brain when you adopt this as an approach? David, I should have paid you for this question. Because it allows you to use my prompts that I really like to use. So if you go to the PBO webpage and you look at the last FAQ, it basically says, because somebody has actually really asked me that before, is it a coincidence that this coincides, that it's basically the same as lead oxide? And the answer is absolutely not. Because lead oxide is not just a substance, or lead is not just a substance that caused the Roman Empire to fall, although this is arguable, but it also takes objects such as this one here, which is, you know, a plaything made out of glass and pretty imperfect, and makes it into nice sparkling things such as this one here. So PBO, lead oxide, is actually what you put into glass in order to make it stronger, more pliable, and to give it more sparkle. So maybe we leave this as the last official question, because my belief is to say something really provocative, that PBO is exactly what you need to put into your software development in order to put the sparkle in. All right, thank you very much. Yes. Many of these ideas have been exploring the rules, right? Excellent. I was very much cool. Yeah, I think yes. Now the way I just
I know I was in the lab last night when the kids were all playing cards. I don't know if I want to comment on this.
Not doing that by hand. You sure will see the no kidding.
Radical but not in this way. At the same time, with parallel engineering, where the people studying power systems are going to be software development managers. They would say, no, this is a risk.
And the stuff distributed.
Or in the school of business.
I'm hoping that some of the software engineering people here, our software so in any case, I'm sorry if I disappointed you if you were waiting for something more controversial. My experience was that some people look at this and go like, I think now we have the data to back it up, right? But you know, one of the exceptions, one way
think the lecture
well, that is sort of that
that's why I'm waking up every day.
started with the next behind Saturn V, went to the moon. And people are now saying, yeah, I mean, 60,000 humans guys brought to Northrop, you know, with pocket protectors and printed graphs and T-squares and slide rules, and they were able to go to the moon. Whereas now we said, America should back the moon, and everybody says, you're, you know, a lunatic, you know. That's entirely possible present day. It's just too complex. So if this sort of choosing, if you went beyond and saying, here's the 5 alternatives of this giant coin, pick one of the 5, instead it says, you know, we can characterize some similar algorithms. Pick one, and it may turn out that something that works, right? But that's about margin for tuning as well. Yes. And then, so now you're crunching, look when you myriad possibilities, build something that works according to spec. I've worked on this. Well, but with and as the folks said, getting up the non-buggy as well.
So, see, I think what happens, one way in which we've been dealing with this practically is, as I said, a buggy does an alternative, just causes your program to fail and there's a huge penalty. And then the design optimizer will say like, whoa, everybody here starts sitting again, because that was a big pain, right? So in some sense, you can actually automatically stay clear of localized buggy behavior. It's not necessarily the right thing to do, but when it comes to bugs, there's non-actually that we don't find it. That's the first thing. The second thing is, keep in mind that any program from space that I talk about, if they don't have bugs, should actually semantically approach also the proper correction. It's just that this might take 1,000 times longer than that, or this might take a million times more energy than that, right? So clearly we don't want to throw everything with hitches in there, because ultimately this design space is really so huge that not the best optimization technology we have do anything about it, right? So we want to be a little bit smart and use our judgment. But my point is that even if we're smart and use our judgment, summarizing and coding up, we still end up with more than we currently maintain. We still end up with, so instead of earning a lot of stuff that's left by the wayside, not because anybody ever convinced themselves it would possibly happen, not even because anybody believed it would work, but simply because maybe this one here was done a little bit earlier and worked right? And so our experience is if you care about particular flexibility, if you say something the test environment that you have now may not be a whole characteristic, so the first thing is whenever, I mean, then with flexibility and flexibility, be creative about things that are not stupid, but that according to your and my expert opinion may work. That's the point.
It's like drug where drug is originally targeted at a disease that's targeted at other things don't be magic. So in software as well, not throwing away.
Precisely. And you know, dog design is a good analogy, because there often you have it that people go like, it doesn't for that may never be fully elucidated, right? It's the same in software, but then you apply the software somewhere else, you put this compound into this 90 different disease state, and boom, it works, right? So it would be a shame to have lost it. So I'm saying there's a cost to maintaining that flexibility, so that if you make your these numbers, that cost is well worth Human science, human creativity, that's the expensive part. And there's another thing, to be honest with you, I didn't say this talk today, I should have, because that's even more controversial, in fact, which is, let's imagine you and I work and we work on the same performance really matters in my design wins and yours gets lost. How do you feel about that? Now you're a pro, you will say fair enough, right? There was no competition, but if we say no, both designs make it in because mine wins out now, your story problems in that, you're going to feel a lot better about it, right? And how are we both going to feel it in this other responding, so all of a sudden your design gets chosen? They're both going to say, yes, this is great, right?
Well, you know, an actual real world instance of that, 10 years ago, some technologies we're working on user customization.
Like the streaming mode with the
Which could be another use of this, like if you're optimizing the block and dollar sign, but optimizing user experience.
These are the kind of discussions that when I look in the lab.
So, team one worked on it for 18 months. We had a design spec, and the progress was too slow. So team two came in, and their hardcore manager, Big Blue Pencil, right, not going to do this, right? There's that. Right. So, my suggestion time was, okay, start in the maps. This is way down the road, maybe V3. But don't throw this stuff away because they're all ideas. But those I didn't do it every day. But that's the principle. Exactly. It's the same principle. Oh, what can I say?
Choosing with silence set for which applications. The first thing to do is machine learning. They select per program basis.
Was it also the last one?
This is presented.
No, actually this comes from, I gave a precursor to the one that is getting adopted is different from this. It was the complexity ones which we had identities. If you like this transfer, you might like to tell the style. These big audience talks that I don't tend to be so technical. My feeling is, being technical, I would probably lose a third of the audience right away and enjoy thirds of the sideway through, and in the end I would be by myself, and that's fine for a conference, but for a bigger audience like this, my assembly was taking this afterwards to be first. You know, I mean, realistically, you could probably learn this stuff for sure. After you have the intuition, I know that's much it's not just so.
I mean, sometimes I've been reluctant to do it because I felt like there's so much anyway. Here is more accurate because I don't want to hear this.
More accurate. Even if you prepare the new stuff.
I'm not thinking of doing it.
It's not possible. Yes, he says that.
Because it wouldn't be that hard for you to adjust it.
That's what I meant in this scenario. You know, you're a company, you want to really sort of optimize your process of giving the data that you've looked at over the last 24 hours. You can just do that, right? Second one, constantly does this. Absolutely. That's the lifelong learning that you just keep talking. It's not, that's another thing that makes it really worth having the rich systems. Even if things change drastically, as long as these things are fine, you have a chance of finding something good about this too.
Work a lot.
So there's
It doesn't differentiate.
I'm not a complex application. I think I want to learn how I think there's fun. Yeah, I was scared because I thought something something like
less math, no equations, more pictures of the elementary science.
They're reading this too, right? So everything.
One of the questions you gave is I'm curious as to with the mixing application. I couldn't exactly.
We should read everything.
Mixing time.
It's all different.
Yeah, it's certainly kind of like you know, how many different.
I mean, certainly this language extension angle, I've seen nowhere covered. So that's why I kind of went down that road, because I really think in order to...
So we're mixing with the dedication count time and compared to... That was on his website. Well, no, it's, when you expose an interview, this is often.
Currently extending the first channel that way, you can actually say,
It looks like
currently the way it goes
on the original,
just say it's a thing
things are entirely purple.
and then maybe you will all design optimizer for the very first time. The first time it sees this parameter, you have a chance to say more about it, like which is pronunciation and so on, and then you have to never do it again. The idea is to have the language specification
So answering the question, how well
so that you can at least say it's an interval that has to be in this interval, and then you can still give additional description, hints and wedge downs.
The decision uses code with this so you use genetic algorithms or some sort of delivery for
That's why don't it's just something that's just if it's, you know,
exponential.
Yeah, it becomes what's typically called a categorical. So the ordering doesn't matter. And it's this
So a lot of problems, you can just say,
also into conditional
this
things
is
because I
my
didn't
objective
talk
function.
about this here, but if you have these nested choices, then you get parameters that really get used here when you have already made a certain choice.
But
And
there
they
are
also tend to make things a bit more interesting. So
you can also say how
interesting stuff to still explore.
And you want to approximate that.
I'm giving up what I'm doing now.
too rapid.
Yeah, you're giving up the game theory? You might have to give up your insert round.
No, the automatic algorithm.
Thank you. Good. So were you a little bit convinced? Or No, I thank you for your questions. Those were very good. I should have provoked even more, but it's difficult with this crowd. You guys are all so, I don't know.
Right. I still think you want to run a program
Barrier for
That's
this.
all the way you do.
How often do we?
Yeah, maybe. But if you have it, this will help you kind of round that out.
There's no reason that it can't work.
I mean, actually, David, ASP, are all steps in that direction.
Like
That's why we're working with Torsten, because I always
entire
believe
space
in
of
ASP
possibilities
solving, there should be good
would be
applications for this kind of thing. And because they use that solver rather than would be
finite resources, but the problem, the instance is so small, it's solvable in that sense, but it's scales grow is the problem.
I gave a talk in Potsdam once, not on this, but just on configuration, and he was one of the wow, this is really cool, we should talk, we should do things.
Faculty member.
Yeah, but that's also because he has that powerful SAT solver, and he knows that in the context of ASP, that probably was very good in whatever SAT context.
I only
Which we
saw
all use.
you.
Good, thanks for coming.
But anyway, I like how so far.
Yes?
How can we optimize?
So yeah, there is this class of problems for which knowing how well am I doing is intractable.
How do we optimize it
That's not too
manually?
unlike the
If you can't measure the
configuration
objective
sort of
value.
that's sort of the configuration, right? Because we
Okay, I mean, anything that you can assess manually, there's just nothing that you can do. Then the notion of design optimization is ill-defined, right?
That's why, right? Because you're actually running a damn algorithm every
I mean, I would think that with MCMC you can still approximate, right?
And-
You really know the function that when you have
it's crappy.
optimization. I mean, people
Sometimes it
talk about
takes,
having
like,
better
45
algorithms,
minutes.
so they must mean something.
So, but what I'm
That's
saying
a
is that
definition.
objective function,
Who cares about
intractable in the sense that you couldn't even approximate.
And you need a signature.
I'm so sorry, that's not embarrassing.
You mean it takes a long time to get the answer you want, right?
Chelsea, you'll have to pick it up with Chelsea.
Well, it will be extremely
No, no,
noisy.
I won't.
Right, good, thanks.
Thank you.
It's noisy and it's
We
it's
want
very time
performance.
consuming to get a sample.
Sample,
Right.
how
It's
many
not like
concepts
the
running in a
tolerance
sample?
Sorry?
They call it a sample because you run it once to get a sample, but you might want more than one sample.
Yeah, but
How many samples
there is a
do we approve?
philosophical issue here. If knowing how well you're doing is as expensive as solving the original optimization problem,
A couple of samples.
But it can be done though.
Say
If
this is
knowing how well you're doing is as expensive as solving the original optimization problem, how would you have ever solved any optimization problem? How would you have ever made
a
just one
Markov
step?
chain, answering the question, is my Markov chain for this parameter mixing rapidly,
One really bad
is
one.
intractable.
But no, I think you're
Well,
too
unless it
you're
gets
too much on worst
stronger,
case
then
analysis.
yeah,
It's
I'm not gonna
intractable
go back there.
in the sense that it belongs to the same worst case complexity class. But that doesn't mean that in practice the two operations
I'm thinking of this theoretically. I know ways around it because we actually do algorithm configuration for Markov. We do algorithm configuration for mark of change. That's why
Yeah.
that's why I worry about these problems.
Yeah, but I think you worry too
Once
much
it's noisy
because
enough,
really this is where complexity in worst case analysis is highly misleading. I'll give you an example. TSP, symmetrical TSP is nowadays solved
don't
to
believe in worst case
60,000
analysis.
right?
When you say it's intractable,
I'm doing the thought experiment.
How do you work out when
you're saying it's intractable
No.
because it's
I'm saying evaluating
local minimum?
But don't
the objective is as hard as solving the original
Do you mean
optimization
it takes the same amount of time, or do you mean
Well,
it
in
belongs
parallel,
to the same complexity?
granted, is our old method like 5 years old.
Either.
No, but it can't be
Consider
taken the same amount of
every-
time. That's just logically impossible.
So if it takes the same amount of time to know how to do
least
it,
one run,
how do you
the
ever
run-
follow a
one run
gradient?
is
How does
worse
your algorithm improve
than
it?
the
How
equivalent
does
run.
it
So
internally make
say
progress
C
rather than thrashing?
for the
around?
Might be no
Knowing
time.
any-
We might be working complex. In complexity, I know it's true.
Well, in complexity,
Complexity
let's not care
the
about that.
first sample.
Because in complexity,
So
you
the
have
samples
infinite
are-
problems.
it's a blocking
Let's say
pair.
problems that from all that we know
It
are
might be local
interchangeable in
minimum
terms of
only
all
with
their
respect to
complexity
one
class
sample.
results.
And
Like the
once you have
TSP
samples,
and the
it's
QAP,
better.
for example, right? And the
If
QAP
you
is
keep on
totally
coming
hard.
back
You
and
can solve
developing
hard
that, then you will
instances,
run more
meaningful
and more
instances with 100. The TSP can solve instances with 20,000, right?
No, I agree.
So,
all the way.
I mean, I know that if we deal with 1,000 by 1,000 images, the computer vision guys
But,
do,
you know,
there are 2 to the power million possible images that you would
there's-
have to deal with.
There's also a random
But
sampling
no
step
one
in there that
deals
keeps it
with
in
it.
those images
Right.
as time.
You also don't
For
need
me, that's the obvious
right?
example.
Yeah.
If I want samples from space images, I should turn on my TV when not set, turn to any station, and I'll see lots of random samples.
Except that nowadays it's totally black. That doesn't work anymore if you've tried it recently.
Today in my ethics class, I had an example of a DVD store that was collecting people's watching habits and then sending them direct mail. And I had to say, this is a DVD store, which is the place where you rent a little round disc, which has a movie on it.
exactly.
And then they send you direct mail, which is sort of like spam, but in physical form.
Coming back to this objective function, one of the things where it comes in is with your point about creativity.
Yes.
And that's actually key, because coming up with good objective functions is actually the where things get really interesting.
Yeah.
Because I say, come up with an objective function that makes this animated character look like Jennifer Lopez.
No, but I think I agree with you that finding something that, given existing optimization techniques, guides you effectively is a very hard problem and requires a lot of creativity, no question there, right? But I think what this can get you towards is getting a little bit out of the need of even finding a new formulation, essentially, that is amenable to standard practices, because to standard optimization techniques. What I think you might often find is that you can just write it down more naturally and then configure an algorithm that's actually based on that.
I think Anna's point is right. Sometimes you don't even know what you're optimizing. And programming by optimization doesn't help you when you don't know how to optimize.
Actually,
But that's kind of the point,
exactly.
right? Then that's the creativity step.
No,
So then-
I agree with you. No, this is where creativity comes in. So like to give you an
Didn't
example.
you hear Holger say that we should never have creativity?
Oh no, quite on the contrary, I'm all for it.
So like the example like Eric, Eric's thesis was about using these tools for when you have a person there. So
Yes.
like the example of the dinosaur that you want to walk like Jennifer Lopez.
Yes.
You could not come up with that objective function. What Eric does is his objective function is interactive. He shows 2 dinosaurs walking
Sure.
and then asks someone to say
But
which
in fact,
one.
that's so incredibly compatible with this framework because it's built on top of the idea of expensive
Well,
systems.
it's exactly the same framework actually.
So I'm not sure
It's
what
exactly.
I mean,
No, it's exactly the same framework. But what I'm trying to say is that in this case, the objective function is the thing that's being learned. And where the creativity came in was in come up with a UI that allows you to learn objective functions.
There's no question that there's other parts of the software development process that need creativity. I mean, absolutely. I think all I wanted to say is, even when you just want to get a well-specified problem solved, at the point where that creative act has happened, there's room and need for a lot of creativity. And we're currently stifling that. We're currently saying, no, we have to early sort of commit to this, and this, and we don't even ever write down all the things that we explored, we throw away code that was working perfectly fine, and that's a crime.
Nanda, what makes me think is how many research papers and good conferences, AAAI, NAMES, are kind of about we explored kind of an existing space of known ingredients
Like these are
to achieve better performance on a new domain of application.
So I've been working on
That's
this.
not a case where the objective function is tricky. That's not to say that such cases don't exist, but the fact that people think this is research, they need to have a new paper, shows that something could be made better.
I completely agree. I read the blogs on, and
I have a blog. Where is it?
by your emails.
I'd like to read this blog of mine. Cool.
And you guys are not alone working on this.
And if you get spots,
We and the guys in Alberta have been working on this stuff.
be professional.
I think we're just pushing it into certain directions that we were lucky enough to be the first ones, and I mean, it's just the case that previously nobody had optimization technology that could solve the size problems that we can solve, right? That's all there is to it. And I think there has been nobody previously who said, this works well enough, let's make this a design paradigm. Let's just go and, create the tools and the infrastructure that makes it as easy as programming is. We believe that it should be easy to do this.
Really hard.
And that's what we're saying. I mean, in fact, I've said, I think very explicitly, look, here's all the evidence from past literature going down to the 80s that this kind of stuff works. Now it works on a grand scale. We've seen it work in pretty much all areas, in very specific contexts where people create solutions that actually really work in that context. And I mean, hyperparameter optimization, you know this better than I. Until recently, all the optimization methods used were totally primitive, right? I mean, come on, adaptive grid search.
No, there's many factors. I could give you a long list.
Oh,
SPSA is an alternative to the Bayesian methods, and that's been used very heavily.
It still only continues. I mean, you really have to. Once you start using the right tools for that, for hyperparameter optimization, you'll be a lot better than what's currently being done.
Alternatively, we're happy to give you our CPlex environment and see how your tools do it.
Yeah, that's right.
The tools that you're using, like this,
Sometimes some words I
maybe
just, I don't even
parallelize
know
is a
what
new
it's
thing, but the model-based
Those weren't
techniques,
called.
those many folks have been using that for
Absolutely
a long
not.
time.
Have a conversation with Frank.
We've had many conversations.
I myself have used it since 2007 to optimize Markov decision process.
I'm very happy if you could point us to a bunch of existing papers, that do that.
Just go to my website.
I think you're talking across each other.
Yeah.
Like, Nando has of course worked on this,
No, just
but
like staring at
he
it.
has
I
of
was like,
course
I have
not
no
worked
clue
in the
what
large
that
discrete
word
space
is.
that
That goes
briefly
in there.
Exactly.
I have not worked in, I've worked on discrete spaces, I've not focused on large discrete spaces, the kind of problems you guys
to
are
do it.
talking
It wouldn't take that long.
But what I'm saying is, it's all useful now.
The central point here, I think, is not, we just had the idea that optimization can be used to would that somebody else had thought about that, but here we are with the Christmas present.
Yeah, I mean, that has been around for a long
I mean,
time.
that's been around, in a sense, that's been the AI dream from the 50s, right?
Exactly.
Right, but it's
I
also
think
the
idea
whole
instead
idea.
is, here's a way of getting the optimization problem out in a form that is amenable, that doesn't become this crazy thing where you're
but she's
optimizing
getting
over
paid
raw
to,
source code
like,
that,
not teach
that
it.
comes
She's
along with a set of
getting
tools that actually are suited to the challenge that you actually have, where you can actually get to the point where you're thinking, as Holger is, about writing a
I
code.
mean, everybody
I
does.
just don't think there's something else that
Oh yeah,
puts all
I
that together
agree.
to the point where that can be done.
This is basically experimental design meets computer science.
But as seen from space, I don't think there's something new here. I think it's as made real.
She does really bad teaching.
Going through it, like taking it to the level of writing of programming
So even if
languages,
like everybody in 320 ended up failing,
because the
it would
statisticians
like
also
figure
have
it
some
out.
problems with a lot of languages.
Well, and also making it general
Where you
purpose.
could hope to do that
Yes.
is new.
Making it general purpose is new because I'm not aware of any
Oh
approach prior
wait,
to
the
2002.
hope is new, but
No, but
the
like,
challenge
I'm
is
sure
always
if the
dimensionality. That's always been our challenge.
Oh, absolutely.
Even like
That's where I think
70,
absolutely.
but that's the problem is how we go further out.
No,
And
not really.
dreams
The
depends
problem is
on-
also how you go to arbitrary pieces of software. Right?
yeah,
Machine
you-
learning algorithms with hyperparameters are a very specific kind of beast, right? They have their own challenges and they have their own opportunities and their own needs. But
And how do
this
you deal
is
with
actually
noise?
more
How do you
general.
deal with an objective function that gets more expensive
I don't like
the longer the
fact
algorithm
that
takes to run?
it's so
How do you deal with conditionality?
Oh yeah. There's all
Yeah, it's just
sorts.
different
There's all
settings.
sorts of issues like that. What
And
if
these
your
features-
evaluations of the cost
I mean,
function are?
the point is, Nando, these features, once you think about programming
Really hard.
with this in mind, they automatically come out. You automatically get a lot of discrete parameters. For every design choice, you get categorical parameters, and you automatically get this situation where they start interacting in very nasty ways and have conditionality attached to them, right? So you can't do it without that, pretty much. So you are being catapulted by this approach into one of the nastiest applications of optimization, right? And I'm not saying nobody else has ever thought of that, but I think realistically, before our group made a couple of breakthroughs, nobody has been able to show that this can actually work in general.
I think there's a reason why it's been floating around for 50 years.
Oh, absolutely.
No, but I disagree with that. It's used. We've been using it in robotics. Dan has used it in robotics.
But nobody has taken one technique, one actual piece of software like Parallelisation and showed that it gives improvements of orders of magnitude in now I think 7 or 8 different domains. Nobody has done that. I mean, if you can show me a paper that has done that, I would be very interested in it.
But the basic optimization technique has been implemented in a huge range of applications. You just search basic optimization in all the different applications.
Yes. But just try that on something like.
But maybe not the same person. Maybe not the same person. Maybe not the same software.
Try
throw a Gaussian process in this stuff and see what happens.
Exactly.
We've tried that.
That's exactly.
It's just not enough.
You need to go further.
It wants things to be continuous. They're dealing with kind of conditionality, discretization, noise, variation in the response surface, kind of all at the same time. Is just enough of an obstacle that this isn't a practical tool. It's not that it's a complete disaster, but it's not appropriate for the application.
No, I agree. So unless you have, with a GP, you have to have some
unfortunately, it's
But the discrete one, the discrete case is discussed in the basic optimization book of Marcus as well. So that also is not. He did consider the case where he wouldn't use a GP. Oh yeah. Bayesian optimization is applied to discrete optimization in the book of Marcus.
But again, I'm not sure quite what you're saying because
I'm saying you guys have done a great improvement in terms of theory, but I disagree with saying that the first to do this. Incorrect.
So I don't particularly understand.
Andrew's from California.
Oh, okay. First time I saw the slides. But no, I wouldn't say that either. But I think the difference in between matters in terms of whether it makes sense.
What is this for?
This thing as
whatever you want.
I completely agree with this, but I don't agree with your claims as to you've done some improvements. But they've been claiming the whole thing because a lot of people have made it. I think you guys are going to the level of generality.
At some point, it starts to look like a
that is
somewhat
more
different thing. I mean,
yes, I agree. When you start talking about programming,
No. It's nothing like that.
the level at which, sure, you can map one kind of problem to another kind of problem, but Bayesian optimization doesn't kind of give you a textbook to read that tells you how to solve this problem. So in that sense, there was something else to be done, which is too bad because we wasted a bunch of time on our GPs at this thing.
So I agree with that statement.
But I'm going to tell this a little bit later, but if I had given this talk, what I would kind of have said was there's been this sort of long-running desire to do program science. There's been lots of little success stories over the years and some of it part of the application, but we kind of have a way of thinking about the framework and what you should draw the boxes around, what the parameters should be, what the kinds of tools can be to operate on that framework. The minutes of ecosystem in grade school, we're getting traction. And it's not necessarily that any one of these pieces is mind-blowing. The whole thing assembles into a kind of traction-producing machine.
That statement I agree with, and I would totally endorse that statement. But the statement of it is totally something new that we invented.
I've seen you give me on this whole.
Maybe before people look at it as something an aside, something they just doing to solve a basic problem that we're working on, and now this aside is the main thing. So that's the difference.
And I think I should also say something I've had nothing to do with. Holger is, I think, ambitious and clever in having tried to do is really going the whole way with the program languages.
I think that's very
I wouldn't have had the patience to wade into the details. That really takes this to the pattern.
Yeah, we should be fine. I think we buffered in a little extra time.
I can't imagine.
And then,
I mean, Nicholas maybe should be cited because he's not.
Well, if we were
A lot of people might have been saying
whatever you think looks good on you.
Yeah.
Unlike relief.
They might not, but
I think what you'd like to say is, there have been a lot of
No, she said only.
Or your extra, so you like be here for a good person. How are you? Good, how are you? So good to see you. How are you doing?
Yeah, I saw it. It's like Alberta sunset. Yeah, Alberta sunsets always look like that. Almost always. No, I saw it really well actually where I was.
He's like poverty.
Man, who decided? On this video.
Huh?
On this video to optimize the way she distributes so maximize the essence.
Hi, Catherine. Yes, I'm in. Nice to finally meet you. This is Michelle.
hi, nice to meet you.
So we're running a little bit late.
Okay.
Just checking those stats.
Okay, so I'm setting up at the end of the site.
Cool. Hey, Andrew.
Hi.
I'm here. Nice to meet you.
Nice to meet you.
Did you fly another trip?
Well, we had an event yesterday, but yeah.
Okay. Okay. Nice.
Yeah, I was thinking about when you guys did
Two quick questions. Internet and this.
I'm gonna hand these out. Can I hand these out?
I have this giant cool
Yeah.
banner in here, but I need to return it to Seattle. Are you guys stopping in the Seattle office after at all? Good. Okay.
Thank you.
So maybe I'll set it up outside so that people can see.
Yeah.
That things are not in here, and then I'll probably take it down. I don't know if you got my email. I'm not like really super. Okay. I will say that first. Okay. I'll just last episode. Okay. Cool.
like her last time. That's how they want it.
Yeah.
That's what they want.
No.
I don't. Here's some decals.
What's that? It's just a big sticker. So it's like a laptop. Yeah.
So this one over here, is that just?
I see.
I think that should be good.
You should be good. This group is pretty good.
Ah.
You don't go back.
Yeah, it's like a big camera. And it'll be like
Yeah, next time you work at Google, they're like, cheap. I
That's probably the best idea.
Map your world.
You could try using this.
I'll try that.
It's mean. It's so incomparable.
No driving. You're driving now? Okay. It's not too bad to drive. It's 2 hours, sometimes it's border crossing. I think I should get an access. You have to get an access. It's so much faster. Really? Especially when you guys have it.